Section 17.9 on qualitative analysis is a section that is honestly not terribly important. You don't need to memorize the schema that's presented here. You could probably skip this video altogether if you like. But it is kind of an interesting idea. And it goes back to kind of some more old school chemistry. The idea is if you have a sample of aqueous solution and you want to identify what types of cations are present in that solution, then you can use solubility rules to sort of parse out what sorts of cations might be present in that solution. And in modern days, you could take that sample and put it through an atomic emission spectrograph. You could use ion selective electrodes. There's lots of other ways that you could identify not only what's present but in what concentration, and atomic emission is really the obvious, robust, reliable way to do that. But in a pinch, if you just wanted to know, is there lead in my water, is there other metal cations in my water, then this would be a way to figure it out. So here we go. So the idea is you have a mixture of cations. It could be many different cations, and you want to sort of figure out which ones are present. Well, if you add hydrochloric acid, then at least of a list of the 20 or so most common cations, there are only a few that would form a solid precipitate when you add hydrochloric acid. Those are lead, silver, and mercury. You remember their solubility rule for chlorides, bromides, and iodides is that they're mostly soluble except for these three, lead, silver, and mercury. So take your aqueous mixture, add hydrochloric acid. If there is a solid, then filter it out, and you'll know that you have one of these three. And then you take the filtrate, or the remaining aqueous solution, and you can continue your investigation. You keep it under acidic conditions and just add some H2S. Well, that's going to introduce sulfide ion, and sulfides there's actually a whole host of metal cations that will be insoluble with sulfide. And so here they are: bismuth 3, cadmium 2+, copper 2+, mercury 2+, which is different than the mercury 2+, lead 2+, antimony 3+, tin 2+, and tin 4+. Okay, so you add H2S under those acidic conditions. If you have a precipitate, filter it off, and you'll know you have one of these metals. And then take the filtrate, and you can continue to analyze it. And so now you add something like sodium hydroxide to turn your conditions basic. You already have some sulfide in solution, but maybe you want to add some more, just in case all the sulfide was taken up forming new precipitates. So you add H2S under basic conditions. This is just continuing down our tree here. And so this third group are metal cations which will form precipitate under basic conditions. And to be honest, I believe these are forming hydroxide precipitates, not sulfide precipitates. So making the conditions basic is important because what you're doing is putting the hydroxide concentration high enough for these to form hydroxide salts, solid hydroxides. Common ion effect, like we discussed earlier, the pH can affect the solubility of different substances. Under acidic conditions, hydroxide salts tend to dissolve. Under basic conditions, they will crash out as a precipitate. And so you add something like NaOH to make the conditions basic, and here we have aluminum 3+, cobalt 2+, chromium 3+, iron 2+, and 3+, nickel 2+, manganese 2+, and zinc 2+. So that's a third group. And if a precipitate forms, then you know you have one of these 8 metal cations. Filter it off, and then take the filtrate, and you can still do more. You can add carbonate or phosphate. So barium, calcium, magnesium, and strontium, these are the heavy group 2 cations, and they are still soluble with hydroxide as long as the hydroxide concentration is kept to a moderate value. Calcium hydroxide will crash out, in particular if you get the hydroxide concentration too high, like concentrated sodium hydroxide. But anyway, if you add calcium carbonate or phosphate, then these will precipitate out as group 4, and so if a precipitate forms at this point, then you have one of these 4 cations. Filter it out, and then what could possibly remain in solution is lithium, sodium, potassium, and ammonium. And this is as far as your textbook goes. Now there are ways to get more sophisticated, like if you had NH4 plus present in solution and you make basic conditions, then that will convert the NH4 plus into NH3. NH3 is volatile and it has an odor, so at this point you could actually sniff your solution carefully, and if you smell ammonia, then you had NH4 plus. And then you may recall some flame tests where you would dip glass stir rod in your solution and then stick it in a flame and observe the flame's color. Potassium produces like a purplish color, and sodium produces a yellowy orange color, a very bright. Lithium will also produce a color. I forget what it is off the top of my head, but it's a lot more faint. Anyway, and with the rest of these as well, there are more sophisticated ways to really suss out which cation among those large groups are present in solution. So there are other schema that use the same principles of solubility and such, but apply these tests in slightly different orders or slightly different, or add like intermediate steps to refine the technique a little bit. But the basic idea is if you're careful with what you add and when you add it, then you can separate cations into these different groups and get an idea of what cations might be present in your unknown solution. So kind of a fun idea, and I don't want to give it any more time than that. So that's it for 17.9. You will not be tested on any of this directly. Just, you need to know your solubility rules, and you need to know reactions that cations can undergo, acid-base reactions and precipitation reactions and such, but I won't be testing you on how to perform qualitative analysis at all.